In the previous lecture, I had derived an energy functional for the total free energy of a static meniscus. The energy functional further depended on the function h of x, which describes the shape of the meniscus, the unknown shape of the meniscus. We had two primary contributions to this. The first one was a surface energy, and the second one was gravitational potential energy. We have a third term as well, which is coming from the changes to the surface energy of the solid at the solid. But we will see that this last term that you see on your screen will enter into the so-called boundary condition at the interface, the so-called Young's law. But the first two terms in the integrand, where we had to integrate the surface energy and the gravitational potential energy over the length of the meniscus, we had said that this term can be written in a compact form as f of h comma hx, where h is the height of the meniscus and hx is the derivative of this height. Remember that this is a static meniscus. Now, I had also motivated that to study problems like this, where we want to extremize this energy functional, we have to use calculus of variations. Now, what I will do in this lecture is that we will show that this function f of h comma hx has to satisfy a specific equation called the Euler-Lagrange equation. This is arguably one of the greatest advances in the field of applied mathematics, and it has wide range of applications far beyond the original intended application for which the Euler-Lagrange equations were developed. We'll see a few examples and then we will proceed with deriving the Euler-Lagrange equations. So the motivation for us is fairly straightforward. We want to minimize this the free energy, but this is not the only problem where we would have a minimization problem. We have other kinds of minimization problems. So let me define some of the other examples. Other examples of minimization could be, for example, you have distance between 2 points. Okay, this is literally a minimization problem. So you have let's call it as A. So let's say we have a point x A here and another point B here, and what we want to do is we want to ask what is the shortest distance between these 2 points. Now obviously the answer is a straight line, but we could also have other paths. And we could ask, can we prove that the shortest distance is indeed a straight line? So how do we do this? For example, one way to do this is to say that I will go from point A to point B along some arbitrary arc. So I have an arbitrary arc, and along this arbitrary arc I will take 2 points here, and these 2 points, if I say the distance between the 2 points is dx, if the horizontal and the vertical distances are dx and dy and the arc length coordinate is ds, then we clearly know that ds is square root of dx square plus dy square, and this is dx times 1 plus dy by dx whole square. So the minimization problem essentially now becomes find out the distance, find out the path that a particle has to take to go from point A to point B, or what is the shortest path from A to B, what is the distance, the minimization, we want to minimize the distance. Okay, So this is nothing but going from A to B ds. And A to B ds is simply x1 to x2, where this point A could be x1, y1, and the point x2 could be x2, y2. We want to just minimize 1 plus y prime square dx, where y prime is dy by dx. So notice that s of y of x is a functional, because and it in turn depends on the function y of x. The idea is that we want to integrate from x1 to x2 this quantity square root of 1 plus y prime square to get s of x, correct? So this is almost a trivial example or a simple example. Let's look at a slightly more interesting problem. This is the so-called brachistochrome problem. So this problem was originally postulated by Johann Bernoulli. It is said that Newton solved this problem in just one night, and Bernoulli proposed this as a challenge to mathematicians. The problem essentially is as follows. You want to go from point A to point B, but now there is a string that is connecting point A to point B. And on this string is a bead which is traveling, frictionless bead. A bead is traveling in a gravitational field without any friction. So the question that you want to ask is, what is the minimum time? This is a minimization problem. Minimization of time. The question is, what is the minimum time it would take for a frictionless bead to travel along a string from A to B? So, and the question is, what is the shape of such a string? What should be the shape of such a string so that the time is the minimum? Okay, that's the key question. So how do we do this? So we say the time, again, now time is the functional. It depends on the unknown shape of the string that is connecting A to B. And if we want to minimize the time, so what we do is we have to go from A to B ds over V. This is again V of x dx, okay, or V of x comma y rather, okay. So A again is, you could, let's say you could go from point x1 y1 to a point x2 y2, and as you go from A to B, the time that you get should be the minimum. So if you naively think about it, I mean, it would look like the shortest distance is a straight line, but if you actually release a bead in the shortest distance, you will not be minimizing the time. There are other shapes that are possible, and this is what perplexed several mathematicians. It's a very, very important problem because it was a fundamental problem which led to the development of the subject of calculus of variations. So we can mathematically state this as follows. I want to go from ds, we've already calculated. ds would be 1 plus y prime square. Gravity would just be square root of 2g h, where h is basically the height that the particle has taken from the point of release. So that will be 2g h. So if the particle has been released from point A with zero velocity, then we have y1 minus y, and we want to go from a to b, so x1 to x2. The unknown that we will have to do is we have to determine what is this function y of x. So in other words, what we again have is a problem of the form integral x1 to x2 some unknown function f. It could be a function of x, y, and y prime dx. It's of this form. So in other words, the functional capital T depends on another function. This is the Brachistochrone problem. There are other examples as well. We want to minimize the shape of a hanging rope. Minimize the energy of a hanging rope. This is also called the catenary problem. So the statement of the problem is fairly simple. So you have, let's say, a fixed post here and another fixed post here. So you have a rope between these two fixed posts, and the question is, if the rope is having its own weight, what is the shape of this rope? Okay, so again we could post it as a minimization problem. Here the rope is going to take a shape such that its potential energy will be minimized. So now we have J. Let's call J as the potential energy. J of y of x. This would be going from x1 to x2. Rho A is the cross-sectional area, G, and the position of the rope, ds. So this is nothing but x1 to x2 rho A y into square root of 1 plus y prime square ds. Now we have to also, this problem is ill-defined if we don't state the length of the rope such that, subject to the constraint, the length of the rope, let's call it as capital L, the length of the rope which is going from x1 to x2 ds. ds would be 1 plus y prime square is constant and prescribed. Okay, so the idea is, for a rope of a given length L, capital L, what is the shape that the rope takes when it is in a gravitational field? Now we know that the ropes do hang like this. You would have seen this in suspension bridges, in electrical wires, and so on. Clearly the shape is not a straight line from point A to point B. It is basically, again, A is x1 y1, B is x2 y2. It's clearly not a straight line. You see that the ropes hang like this. The shape is called the catenary, and the problem is, what is the shape of this catenary, which will minimize the total potential energy of the system. Now we can look at another fourth example, which is, this comes from Lagrangian mechanics or particle mechanics. Here the idea is that a particle, so this goes back to Lagrange himself. So Lagrange showed that a particle will take a path will always take a path that minimizes the integral of the Lagrangian, integral of the difference between kinetic energy and potential energy. So in other words, the problem is as follows. So we want to do, maybe I'll write it this way. So we have Q of t. This is going from, let's say, T1 to T2. You want to minimize this quantity. This quantity, let's say, is called L, and this is T, Q, and Q dot of dt, where Q is displacement of the particle and Q dot is momentum, displacement of position, and the Q dot is the momentum or the velocity of the particle. So this is L is the Lagrangian. It's called the Lagrangian in honor of Lagrange. And this is nothing but the difference in kinetic energy and potential energy. Now, if you look at all these problems, including the original problem that we stated, so we have 5 examples. We have the free energy of a static meniscus. Then we looked at distance between 2 points, the Brachistocone problem where we are trying to find the shape of a curve along which a bead travels such that it minimizes the time. We are trying to find out the shape of a hanging rope of a known length such that it minimizes the potential energy. And finally, we are also trying to find out what is the path that a particle takes such that it minimizes the total integral of this quantity called the Lagrangian. So in all these problems, something is common. What is common? All the other above problems can be written in the form some j, which is a functional j. This is a functional. Some j is equal to x1 to x2 f of x, y, y prime dx, where y of x is a function and y prime of x is nothing but dy by dx. So we have, the goal is we have a functional j and we want to minimize this functional j, or we want to extremize the functional j such that and the idea is we want to extremize this functional j, and the goal is to determine the shape y of x. So y of x for us, we can now say y of x is the extremal of the functional j of y of x. That is, you can say y of x optimizes j of y of x. So you can see that minimization problems are common in optimization as well. So this is, you can think of it like an optimization problem. Okay. The idea is as follows. So let's consider some unknown 2 points in space. So let's say this is x1, y1. Let's call this as point A. And we have a point B, that's x2, y2. And what we want to do is, we want to find out the shape of a function. So let's say there is some special shape going from here to here, okay, a to b. And this function, let's call it as y of x. This is the function that we are looking for. Or in other words, it's the function, it's the extremal of y of x. Okay, we are looking for this y of x. Now, how do we go about doing it? Now, what we will do is to look for this function y of x. We will first say that let there be a function, we'll call it as y bar of x, which is nothing but y of x plus some deviation from y of x. So this is this epsilon eta of x tells us the distance. Let's say there's another quantity here. So at any point, this distance is given by epsilon eta of x. Now clearly, if eta of x can be arbitrary, it depends on the problem. But epsilon, as clearly epsilon goes to 0, epsilon is basically the deviation from this extremal that we are looking for. When epsilon goes to 0, we get the function y of x that we are looking for. Okay. Now we also want to ensure that this eta of x that we have described, eta of x, this is the variation of y of x. Okay, it's an arbitrary variation. It's an arbitrary function. And we also know that this eta of x should be chosen such that we start at a and we want to be at b. So a and b are fixed points for me. So because a and b are fixed, we also require that eta of x is such that eta of x1 and eta of x2 is 0, meaning there is no variation at the endpoints a and b. Okay. Further, we say eta of x should be continuous and twice differentiable. That implies eta prime, eta double prime are also continuous. Okay. Now, let's write down the function again. So we have y of x, we will define as y bar, will be y of x plus epsilon eta of x. Therefore, y bar prime of x will be y prime of x plus epsilon eta prime of x. Okay. We are looking for this functional j of x. For this functional j, let's call it, where it's x1 to x2, some f of x, y of x, and y prime of x dx, right? Now, it's important to note that this j of x, we are looking for the extremum, and we can say that since y of x is the extremum and the only variation is because of epsilon, because the variation is primarily because of epsilon, we can immediately say that j of y bar of x, this is j of y of x. J of y bar of x, the only thing that is varied is epsilon. So it's essentially, it's a function of epsilon. J is a function of epsilon. That's the main thing that is actually varied, because y of x is going to be fixed and we were trying to achieve y of x. What we are varying is this epsilon. So in other words, if we are going to get an extremum, then epsilon goes to 0. So in other words, since epsilon is equal to 0, gives us the function we are looking for, that is y of x essentially becomes y bar of x when epsilon goes to 0. Then epsilon is also an extremal of j. In other words, j prime of epsilon, j prime at epsilon is equal to 0 is 0. So physically what it means is that, let's look at a simpler case. If you were to do a classical maximization or a minimization, what we will say is that here's a function. There is some arbitrary function in space and we want to find out the minimum. So if you want to find out the minimum, we say, I want to find out this location such that this function f at x min, the derivative of f is 0 at this location. So this is x min and this is f of x. Then f prime of x min is 0. So in other words, as you go along the curve, the only variable is x. Okay, and when you hit the minimum, the derivative of the function goes to 0. Similarly, the only variation is epsilon that you're varying. And because epsilon is the only quantity that is being varied, when epsilon goes to 0, we have hit the function, the minimum extremal of this functional. Therefore, j prime of epsilon is equal to j prime when epsilon is equal to 0 should also be 0. And what does this essentially mean? It means dj by d epsilon at epsilon is equal to 0 is 0. This is a key point. We have to recognize that this is true. J prime is not 0 anywhere. It is 0 when epsilon is equal to 0. That's the key thing. Okay. Now we can expand this as following. Dj by d epsilon at epsilon is equal to 0 is nothing but d by d epsilon. This is when epsilon is equal to 0, remember, or I'll put this outside. What is j? J for us is x1 to x2 f of x. Now we have y bar because we have epsilon there in it, y bar of x and y bar prime of x dx, and this quantity is when epsilon is equal to 0, and we know that dj by d epsilon is 0. Okay, so this essentially, if you use the Leibniz rule, we essentially have dj by d epsilon at epsilon is equal to 0 essentially becomes, I can take it inside, x1 to x2 del by del epsilon of f of x, y bar and y bar prime of x at epsilon dx. Okay, this is equal to 0. That's what we want. Okay, now how do we basically proceed further? We can use the chain rule here. We are taking a partial derivative with respect to epsilon. So we have, if you use the chain rule, we simply have x1 to x2. So the first is we have df by partial f by partial x into partial x by partial epsilon. That's the first term. And x is not a function of epsilon, so this term is 0. Then we have partial f by partial y times partial y by partial epsilon. That's the next one. So I made a small error here. This should be y bar. And finally we have partial f by partial y bar prime and partial y bar prime by partial epsilon. So we have all of them. This has to be evaluated at epsilon equal to 0, dx 0. Now we can calculate each of them separately. For example, we know since y bar of x is y of x plus epsilon eta of x, this gives us del y bar by del epsilon essentially gives me eta of x, and y bar prime of x gives y prime of x plus epsilon eta prime of x. This quantity del y bar by del epsilon essentially gives me eta prime of x. So I have now determined this term here and this term here, the last terms. So now I can simply write integral going from x1 to x2, which is del f by del y bar, and this is nothing but eta, plus del f by del y bar prime of eta prime evaluated at epsilon is equal to 0 of dx is 0. Now we know that at epsilon is equal to 0, y bar goes to y and y bar prime also goes to y. So y bar goes to y and y bar prime also goes to y, and therefore del f by del y bar essentially goes to del f by del y, and del f by del y bar prime essentially goes to del f by del y prime. So I can just replace these terms here with just because remember this is done at epsilon equal to 0, that's why we are carrying that epsilon equal to 0 every time in every step. So I can now replace these bars and just simply write it in terms of y and y prime. So now what do we have is we have x1 to x2 del f by del y eta plus del f by del y prime of eta prime dx is equal to 0. Okay, this is sometimes also called the first variation or in the weak form. Okay, we'll just weak form. It is the what it's called is not relevant for our discussion, but it's still useful to know. Now what we can do now is, it's called the weak form by the way simply because it is not explicitly in terms of eta alone, we also have an eta prime. So one way to get rid of eta prime is, if you look at these terms here, I can use integration by parts. How do I do integration by parts? If you remember your integration by parts, we have, if you have a to b, let's say u dv, this essentially gives me vu from a to b minus a to b of v times du. Okay, so if I calculate this quantity del f by del y bar, only this quantity here, I'm calculating only the second term here, eta prime going from x1 to x2 dx, this quantity will simply be del f by del y prime of eta going from x1 to x2 minus integral of x1 to x2, the derivative d by dx of del f by del y prime. dx. This is the integration by parts of the second term in my expression. Let's this now if I substitute into this, we simply have x1 to x2 del f by del y eta, that's the first term here, dx. Let me just write them slowly. Now if you notice here, this term is also 0 because eta is 0 at x1 is 0 and at x1 and x2. So since eta of x1 is eta of x2 is 0, therefore the first term disappears. What we now have is minus x1 to x2 d by dx of del f by del y prime dx, and this whole quantity is 0. We can combine both of them into one single integral, which is x1 to x2 del f by del y minus d by dx del f by del y prime of eta dx is 0. This is also called the strong form. Okay. Now, since eta of x is arbitrary, that's something that I said at the very beginning, that eta of x is some arbitrary function. Eta of x is an arbitrary function, and therefore for this integral to be valid for all possible values of eta, all possible functions of eta, we require this quantity inside the integral del f by del y minus d by dx of del f by del y prime is equal to 0. So this equation has a very important name. It's called the Euler-Lagrange equation. So it is said that Lagrange worked on this when he was just 19 years old, and Euler, who was later Lagrange's doctoral supervisor, expanded this further and developed a detailed theory of calculus of variations. Lagrange himself has written seminal papers on calculus of variations in his so-called Mécanique analytique. This was, I think, in late 1700s, maybe 1785 or 1788, around that time. Now, this is a very, very important result, and now we can actually make a general statement about this equation. So we say a general statement that we can formally write is as follows: a necessary condition to extremize the functional j of y of x is for the function capital F of x, y and y prime to satisfy the Euler-Lagrange equation. Okay. So this is a very, very important step in our analysis. We don't have time now in this lecture to apply this to the static meniscus problem, which we'll take it up in the next lecture. But I would like all of you to try and apply this Euler-Lagrange equations on our energy functional that we had derived. Remember the energy functional that we had before was f of h comma hx. I've written it as h and hx. So the energy functional that we are looking for is this energy functional E of, let me just say, h of x. So we want to find out the shape of the meniscus h of x such that the total energy of the static meniscus is minimized. And for this function f of h comma hx, which I will just highlight here for your reference, this function f of h comma hx satisfies the Euler-Lagrange equation. So we already have derived the Euler-Lagrange equation just now. So I would like you to try and substitute this function of f of h comma hx into the Euler-Lagrange equation and see what you get. But we will do this in the next lecture. Thank you.